Okay. Good morning. Welcome to our science seminar for today. I'll ask you again, turn off the Wi-Fi and your mobile devices so that recording is interrupted. Today we have with us a guest from across the border. He traveled in all the way from Louisiana to get a passport stamp. He came here into Texas. Okay. And, oh boy, I hope I can say his name right. I've been practicing this morning with Dr. Wesley, but we'll see if I did. Tibor, Szarvas. Is that good? Close enough?
Szarvas.
You're very kind.
Thank you.
Okay. And he comes to us from the Department of Mathematics of Louisiana State University in Shreveport. He has a PhD in mathematics from the University of South Carolina in Columbia. And he did his dissertation in uniform LPW spaces, whatever that might be. Maybe he'll tell you a little bit about it. He also has a master's in mathematics from the Joseph Attila University in Hungary. And down here, it tells me someplace that he speaks a number of languages, including Hungarian, Russian, English, and German. So, sprechen Sie Deutsch?
Jawohl.
So we are very happy to have Tibor with us today. And I would also encourage you to join us for lunch if you're interested in logic or in graduate programs in math at Louisiana State University. And let's give Tibor a warm welcome.
Thank you very much. It's a pleasure to be back on your campus. Thank you for inviting me, Dr. Tibor, Dr. Wesley, and thanks for that wonderful introduction. It was worth driving here just for the introduction. Gracious exaggerations. By the way, the Russian is a little bit of an exaggeration. I would have trouble speaking it, but anyways, I have some background in it. Let me start out by asking everybody, are you excited about Jesus Christ?
Yes.
Yes, He is the truth. Amen? He is the truth. Okay, I'm going to talk about Him, about the truth, in my talk today. It is a science seminar, I know, and I'm still going to use the word mathematics quite a lot, and logic quite a lot. Is that okay? Will you forgive me? I mean, my excuse for that is that mathematics actually is the foundation for scientific thinking. Okay, so by me using mathematics, mathematical thinking, and logic, you can switch out the word and just think about science if you want to. But mathematics is part of the sciences. It is foundational to the sciences. And so I'm going to start out by discussing a little bit of how students can benefit from mathematical studies. Now, I hope everybody got a handout. I'm not trying to be low-tech or anything, but I have brought a Word file, actually, and I'm going to scroll down and move as we go along. I expect your active participation in the process, if you don't mind. There is a Chinese proverb that says, I hear and I forget, I see and I remember, I do and I understand. I always would like for my students to actively participate in the process in order to keep them engaged. So you will see some blanks in the handout, which I ask you to fill in as we go along. If I skip anything or if I go fast, feel free to raise your hand, but I try not to. So having said all that, let's get started on the first page and discuss what are some of the benefits of studying mathematics. Studying mathematics, number A, not sure if you're expecting this, maybe you are, helps you conform to the image of God, inasmuch as it does the following. Helps conform to the image of God, inasmuch as it does the following things. Number B, it improves mental clarity. C, studying mathematics develops an appreciation for correctness and accuracy. How many of you know? you're penalized if you're being incorrect in the middle of a math problem, right? Number D, studying mathematics helps you. It teaches perseverance in a difficult task. Can I get a witness? Have you ever tried to solve a problem, difficult problem, and you needed perseverance to get to the end of it, right? Only to find out that your answer was incorrect because it's not the same as in the back of the book. And then you went back to the problem, you resolved it, you got the same answer, and then you had to go back to the book and finally realize that the two are reconcilable because they are equivalent after all. So you spent all that time for nothing. Anyways, yeah, that happens sometimes. But that's part of the fun, is it not? Number E, trains in endurance and discipline. How many of you know? Even the Apostle Paul talks about it. Followers of Jesus need those qualities. F, mathematics, studying mathematics reminds us of human limitations. And I will talk more about that later. Reminds us of human limitations. Number G, studying mathematics reinforces Scripture's warning against reliance on our own wisdom or understanding. Proverbs 3:5. Next, very important, mathematics teaches the habit of proceeding by principles. There are principles you've got to follow as you proceed. And that's very biblical. Because the Bible lays down principles for us, for living. But it doesn't always go into specifics. For example, I never seen a Bible verse saying something like, thou shalt not text while you drive, or, thou shalt not. No, but the principles are there. And then in the light of the Holy Spirit, the wisdom that He gives you, you can determine how to live in obedience, following the principles laid down by the Bible. Also, mathematics penalizes you for digressing from the principles, right? Number I, mathematics provides the basis for scientific thinking. I have mentioned that already. And I put the word scientific in parentheses. You know why? Because I happen to believe that mathematics provides the basis for thinking, period, for human thinking. Some have said mathematics is nothing other than human thinking at its best. People think, math is only number crunching. No, mathematics is much more than that. It's human thinking at its best. And you know what? If that is the case, then you can use mathematics even in the defense of our faith. Because people argue. People call us Christian scientists. They call us bigoted and narrow-minded. To that I would respond to my non-believing scientist friends, you know what? I think you're bigoted because you're not willing to consider other systems of axioms. But I will talk about that a little later. But that's number J. It is helpful even in the defense of our faith. Now, there are two requirements in order for us to reach valid conclusions in our scientific pursuits. There are two essential things. First, we need correct or true foundations, starting points. And second, we need correct or consistent logic. In other words, to stay relevant in our academic pursuits, we need to stand on the truth as foundation, and then we need to use correct logic as a vehicle to carry us towards conclusions. If you're lacking either of those, you're in trouble. For example, if you're lacking consistent logic, you may be standing on true foundations, but your logic is not consistent, you will be in all kinds of trouble. If you lack the foundations, your logic might be consistent, but you won't reach correct conclusions. In other words, my point is that in a formal system of thought, which I will discuss in a few moments, in a formal system of thought, if your foundations are incorrect, even though your logic might be all right and sound, you will reach from silly foundations, you are guaranteed to reach silly conclusions if your logic is correct. I mean, I admit this example is silly, but someone once was trying to do a little research on the wind, so how wind comes about. And of course, by observations, they made up this assumption that wind is actually caused by the trees. The trees are waving with their branches, and that's what causes wind. Okay, with that assumption, of course, using sound logic, they came to the conclusion that therefore there cannot be any wind on any planet that lacks trees. Of course, this is backed up by our scientific, we've been to the moon, we sent spaceships to the Mars, and indeed we found that there is no wind up there. Why? Of course, because there are no trees. Okay, logic is sound, conclusion is silly. Why? Because the foundation was silly. Okay, now what is a formal system of thought? Let me define that for you. Now, none of my definitions are absolutely correct in the sense that I wouldn't print them in a textbook, but for our purposes, a little intuitive, these will do. A formal system of thought is a collection of basic concepts. That's your first blank. Basic concepts, axioms, definitions, true statements, and the logical system holding these together along with the symbolism to represent them. In other words, you need to be able to communicate. You need symbols to communicate what you're thinking. Some examples, geometry is my favorite. Obviously, I'm a little biased towards mathematics, but there are lots of others, theoretical computer science, theoretical physics, lots of others, formal systems of thought. Let me use, if you don't mind, geometry as an example. I'm going to use Euclidean geometry, which we are used to. Lines are straight and, all that kind of good stuff. It is based upon, first of all, undefined concepts. One example of an undefined concept is a point. You say, Dr. Szarvas, I know what a point is. Here is my pencil. It's really sharp. I touched the paper with it. That's it. That's a point. Well, I tell you that unfortunately is not a point, because if you look at that under a magnifying glass, a point is not supposed to have dimension to it. No size, no diameter, no nothing. In other words, you can say, well, a point is something that's really nothing. Okay, it's infinitely small, so it's there, but it's not there. How would you define what a point is? Actually, mathematicians have tried. They all failed. They said things like a point is a location in space. That's pretty good, right? Location doesn't have dimensions. Sounds good, right? But there's a logical problem with that. If you say a point is a location, then go ahead and define location for me. Okay, point is something that has no dimension. Some have said a point is the beginning of a line. Okay, but I mean, where is the beginning and what's a line? So that has problems. They said the point is that has no part. Or silly things such as a point is that of which the middle covers the end. In other words, none of these definitions succeed. In order to build a consistent theory, point will remain an undefined concept. So there it is, point, undefined concept. Infinitely many points make up a line. Okay, they are sitting next to each other on the line. I mean, I could give you a lecture on what next to each other means, because there is no such thing. But I mean, how come infinitely many points, which have no dimension, make up a line that has a length infinite? Okay, not going in there, but uncountably many points form the line, which again we don't know what it is because we didn't know what points were either. Okay, so the line is going to be an undefined concept. Plane. These basic concepts in Euclidean geometry that Euclidean geometry is based on. They are undefined concepts. Now, we link some of these undefined concepts with axioms. Axioms are true statements that are true because they are accepted to be true. They have no proof. For example, in Euclidean geometry, the fact that 2 points determine a line. We don't prove that. It's accepted as true. Okay, so why is it true? Because it's an axiom. And there are others. For example, in a plane, through a point not on a line, okay, I'm in a plane now, through a point not on a line, there is exactly one other line that has no point in common with the first one. We call that parallel. There's exactly one parallel. That is called the Euclid's parallel axiom. It has no proof. It's an axiom. People try to prove it, but they all fail. You know, there's only one parallel line, and then people say parallels meet at infinity, right? That's silly. I mean, there is no infinity is not a place. I mean, you can never find where they meet. They are parallel, and they don't meet. It's like the two guys who were walking down the railway tracks, you know, in an attempt to try to find where the tracks meet, and they were walking and walking and day and night, and gradually they got exhausted and dehydrated, but they were determined to find that point where they meet. So they kept going. I mean, finally they barely had any power to walk anymore, so they were crawling. They go like, we'll never get there. I can't believe we ever get there. When are we going to get there? One of them looks back and he says, hey, we already passed it. Okay, so anyways, these are axioms. Now, once you have your undefined concepts and your axioms, then you start building concepts, okay, defined concepts, such as, for example, you can define what a straight line segment is and stuff like that. You can define what a triangle is, and then you can prove statements using your axioms and your concepts. You can prove things such as the interior angles of a triangle add up to 180 degrees and those kinds of stuff. So you prove more and more complex statements using your undefined concepts and your axioms and statements that you have previously proven and definitions that you have previously made. And you keep building this theory, this formal system of thought until it becomes beautiful and complicated and you reach hopefully valid conclusions. But all of this formal system, has to be held together by a consistent logical system. Consistent, I mean error-free. Otherwise, we are in all kinds of trouble. Now, what is logic and what are some errors in logic? I'm going to go through a list just to illustrate for you what can happen if the rules of logic are violated. And unfortunately, this happens all the time in real life. I mean, just go out. If I were your professor, I would give you a homework assignment, a project. Go turn on the TV, read the newspapers. I hate to mention political debates or whatever, but even in personal conversations, how many times the rules of logic are violated? We are going to list a few examples, few common examples. Errors in logic are called fallacies, so I'm going to list a few common everyday fallacies. Number one, the first fallacy is called appeal to popularity. I'm not picking on any make or model of automobile. I apologize. I know some of you probably drive Fords. This has nothing to do with Ford. It's just an example. But imagine that in an advertisement they say Ford makes the best automobile in America. After all, more people drive Fords than any other American car. I mean, that may be true, but does that make a case? In other words, here's the logical essence of all of this. Just because a great number of people believe that a proposition is true, that doesn't make the proposition true. It could be true, but not because a lot of people believe in it. This is called the appeal to popularity fallacy. Number two, the fallacy of false cause, hasty generalization. I brought two examples. They are slightly different, but the first one is more like false cause. The second is hasty generalization. Let's look at the first example. I placed a quartz crystal on my forehead, and in 5 minutes my headache was gone. The crystal alleviated my pain. Problem? Just because an event precedes another event, it doesn't mean it caused it. And the second example, 3 cases of childhood leukemia occurred along the street where the high voltage power lines run. The power lines must be the cause of these illnesses. It's a similar situation. Just because something happens before another event doesn't mean it causes it. And besides, this sample of 3 cases is not even sufficient. A lot more analysis has to be done in order to prove or reach a proper conclusion. Number 3, see how many times you run into this. The fallacy of appeal to ignorance. Appeal to ignorance. Here is an example. Scientists have not proven that extensive use of cell phones will have an adverse effect on human health. so you don't have to worry at all. This argument has no merit. Why? We don't know what they will prove tomorrow, but essentially, the lack of proof for a statement doesn't mean that the opposite of the statement is true. It's just a plain old logical error. Next, number 4, the fallacy of limited choice. Happens all the time. Here's an example. If you don't support the president, then you are not a patriotic American. What is the logical problem with this? The problem with this is that it artificially limits the choices to only 2 kinds of people. Patriotic ones who support the president and unpatriotic ones who don't. You cannot do that. I mean, in reality, there may be many more choices, possibilities. For example, there could be patriotic people who do not support a particular president, or unpatriotic ones who do. You cannot force limited choices to your hearers and make an argument based upon that. I mean, an example of the same thing that happens during personal conversations and arguments, is especially if, after a while, the participants become a bit frustrated with each other and somebody says, "You're wrong, so I'm right." Okay, again, just because the first person is wrong, it doesn't mean I'm right. Again, limited choice. Maybe both of us are wrong. Okay, so there are more choices than the speaker tries to make it out. Next, the fallacy of appeal to force. Imagine the following scenario. A particular candidate before an election says, "If my opponent is elected, your tax burden will rise." This has many problems. First of all, it is just a subtle form of blackmail. I mean, just read it and just think about what it means. What they are actually trying to say is, if you don't vote for me, if you don't think like me, you will pay for it. Or you will be, in some cases, intimidated or ridiculed. But not only that, but logically speaking, they say nothing about what will happen if the opponent is elected. Maybe the opponent is going to raise taxes even further. They say nothing about that. Number 6, the fallacy of personal attack. Personal attack. In Latin, this is called ad hominem, which means, in Latin, it means to the person. Here is a somewhat silly example. Person A, person B, conversing. Person A says, "You should stop eating foods high in saturated fat every day, because it will have a long-term negative effect on your well-being, and it is real bad for your cardiovascular system." Person B in reply, "Well, I have seen you eat a triple bacon cheeseburger a couple of days ago with my own eyes." Okay, I mean, this happens in conversations, unfortunately, but what's the big problem with it? If you look at the retort by person B, whatever person B says has nothing to do with the point made by the first speaker, but much rather it's a personal attack on the speaker. Rather than logically arguing with the proposition, the second person chose to attack the speaker. I mean, this happens in more brutal ways. When the two proverbial, people argue with each other, they get slightly frustrated, and unfortunately, sometimes the argument might even finish with something like, "Well, I just can't talk to you. It's impossible to talk to you. You are an idiot." I'm not going to finish that word. You are I'm not sure if you heard, but Ken Davis, a Christian comedian, was talking about a pastor who got frustrated with his lawnmower in the yard. And I can't exactly remember the story word for word, but the pastor was talking about the lawnmower kept breaking down or whatever. And he goes like, "The bad words started forming in the back of my head. The neighbor trying to embarrass the pastor. He says, "What word?" The pastor goes like, "Well, the one you're thinking about will do." Okay, so anyways, unfortunately, some of these debates, arguments between people can get heated, and the sad thing about it is that a lot of times they are riddled with logical fallacies. Next, number 7, the fallacy of straw man. Straw man fallacy happens when somebody, the speaker, creates his or her own artificial phenomenon that they argue against rather than the actual point they need to be arguing against. One example is someone might say, "We know that there is no such thing as an absolute truth because Einstein's theory of relativity proved that everything is relative." Right? What's the problem here? The problem is that Einstein's theory is only valid for the physics of light, motion, and gravity. Not everything. So the speaker either does not understand the theory at all, or, worse yet, is trying to deliberately distort its conclusions. Two classic ones, number 8 and 9. Number 8 is the fallacy of denying the hypothesis. Every mature believer understands this doctrine. Johnny understands this doctrine, so Johnny must be a mature believer. Is that a valid conclusion? It sounds okay, right? I mean, mature believers understand the doctrine, and Johnny does, so he's a mature believer, right? Sounds right, but it's logically faulty. Because if you imagine, if you examine the premise, every mature believer understands this doctrine, this actually is an implication, A implies B type of statement. It says, if you're a mature believer, then you understand the doctrine. A implies B. Now, Johnny understands the doctrine means that B is true of Johnny. Can we conclude that, therefore, that A is true? In other words, what we are doing, in essence, is we are going from A implies B to B implies A. We are simply reversing the implication. Cannot do that. I mean, most implications are not two-way implications. Number 10, somewhat similar. 9. Denying the antecedent. Number 9. Example, if you like the book, you will love the movie. But I didn't like the book, so I'm not going to like the movie. Again, it sounds believable, probable. I mean, if they didn't like the book, probably they won't like the movie. But is this correct logically? It turns out that it is not. Because what it is really, again, the first statement is an implication. If you like the book, A implies B, you will like the movie. But I didn't like the book. In other words, no A is true. Does no A imply no B? In other words, can you replace an implication, A implies B, by the implication no A implies no B? And the answer is no, you cannot do that. Because maybe the movie is so great, I will like the movie so much, it might even change my mind about the book. And number 10 is my favorite. I mean, I'm careful to say my favorite because actually it's one of the worst. It's called the fallacy of circular argument. Circular reasoning. Or sometimes it's called begging the question. I always tell my math majors, if I see any trace of this in your proofs, first of all, I'm going to use up all my red ink on your paper, and second of all, it's an automatic 0. What is circular reasoning? Circular reasoning is when you are building an argument, and in your argument, you are using the very conclusion or part of the conclusion you're trying to prove. Here's a silly example. I'm going to use a circular argument to prove that kangaroos don't wear suspenders. Okay? Here it is, the argument. Kangaroos don't wear suspenders. Proof. Why? Kangaroos don't wear suspenders because kangaroos don't even wear pants. Kangaroos don't wear pants because they are hopping around all day, and they would lose their pants by hopping around all day because they don't use suspenders. Okay, you see the problem. I used in my proof some of, or actually all of, what I needed to prove. But this can be done in more subtle ways. I mean, here's a nice sounding statement on the screen before you. It says, society has an obligation to shelter the homeless because the needy have a right to the resources of the community. Sounds good, right? I mean, but what's actually happened, if you examine the parts of the sentence, we are just saying the same thing twice. I mean, the first half of the sentence, which is actually supposed to be the conclusion, is the same as the second half, just slightly disguised. In other words, the reason that this is called begging the question is because we are begging the listener to accept what we say by saying it twice. I mean, if you think about it. We have an obligation because they have a right. I mean, it's essentially the same. And it happens in real life all the time. Okay, so we have seen a few instances when the rules of logic fail. And I must admit, I may be doing a slight disservice to you, because inasmuch as I managed to open your eyes to some of these fallacies, you go out and you keep listening to advertisements, reading in newspapers, whatever. You will be bothered by fallacies, maybe more so than up to this point. However, I think that's a good thing because we need to use discernment in this world. This is the information age. We need to use discernment, God-given discernment, to distinguish between right and wrong. And logic is an excellent vehicle. It's an excellent tool that helps us do that. What is logic after all? This is my little definition. Logic is the science that investigates the principles of correct or reliable inference. It examines the rules of reasoning applicable to any branch of knowledge. Very important. Rules of reasoning applicable to any branch of knowledge. So I'm talking not only math, I'm talking science. I'm talking not even science. I'm talking about any branch of knowledge. What about consistency? A formal system of thought is called consistent if it is free of contradictions. If it is free of contradictions. In other words, not even a single contradiction is allowed. What is mathematical logic? Mathematical logic examines the foundations of mathematics. And I go to the next page, the big question. The big question is whether mathematics is consistent. In other words, is mathematics contradiction-free? And why should we bother? I mean, I'm sure Dr. Wesley and your math professors sometimes, I know because I do it, sometimes when we prove certain things on the board and we prove by contradiction, we reach a contradiction and we say, thereby the theorem is proved because this is a contradiction and math cannot have any contradictions. We haven't found any yet. But is there any guarantee that there are none? I mean, what about 100 years from now? Is anybody ever going to find a contradiction in mathematics? It's a big question. It's a question that we should lose sleep over, honestly. Because if there is one contradiction in mathematics, if it's not consistent, you cannot localize a contradiction. Like, okay, there is a little contradiction here in functional analysis, but that causes havoc in this area of mathematics, but the rest of the math is good. There is no such thing. You have one contradiction in mathematics and the universe collapses. Well, not exactly, but one contradiction. Logic professors are able to prove that from one contradiction, I will say lie, you can prove any other lie. In other words, one contradiction logically implies any other contradiction. In other words, if you have a contradiction in functional analysis, then I have green hair. And that's provable. Some time ago, a logic professor was giving a talk to lay people. And he talked about the basics, the rules of logic. And when he got to this point, he says, from one contradiction, we can prove any other contradiction. One smart lady in the audience was bothered by this, raised her hand, and she says, well, I just can't believe this. I'm sorry, I can't believe that you can prove anything out of one contradiction. He says, yes, ma'am. She goes like, she was a smart lady, she says, well then, prove to me from the fact that 2 + 2 = 5. That's the assumption. Prove to me that you are the Pope. The logic professor goes, yes, ma'am. That's not difficult. He turned to the board and he started out with the equation, writing 2 plus 2 equals 5. He says, let's consider this equation and add the two numbers on the left-hand side. Thereby we obtain 4 equals 5. Now, as we can do with equations, we can always subtract the same number from both sides. So let's subtract 3 from both sides. Thereby we obtain 1 equals 2. We know in mathematics that the relation of equality is a symmetric relation. Whatever that means, it means that we can reverse the sides of the equality. So if 1 equals 2, then we conclude that 2 equals 1. And because everybody knows that the Pope and I are two persons, but because 2 equals 1, therefore the Pope and I are one person, so I'm the Pope. Okay, just one silly example of one contradiction implies anything. So we cannot afford even one contradiction in mathematics. So it is a big question. Now, in the year of 1900, David Hilbert, probably the most famous mathematician at that time, came up at a conference in France. He came up with 10 problems. They are called Hilbert's problems. Later he published more than that. He published 23 problems that were open questions in mathematics, and he anticipated that these very important open questions will be answered, will be proven by mathematicians during the 20th century. Now, some of them have. People won the Fields Medal, which is the equivalent of the Nobel Prize in mathematics, for answering some of Hilbert's 23 problems. Some are still open. But at any rate, Hilbert's 23 problems were very influential in the development of 20th century mathematics. What I'm discussing here actually is Hilbert's second problem. Is mathematics consistent? I mean, Hilbert was bothered by this, and rightly so. Can we prove that mathematics has no contradictions? And that was his goal. He said something like, the axioms that are the foundations of science are not contradictory. That's the goal. In other words, can we prove, using a definite number of logical steps, that we will never get a contradiction? In other words, we ought to be able to prove this, right? Some mathematicians started working on this. There were partial results, encouraging partial results. Nobody got it, but they at least started working on it. It was a big catalyst to the development of logic. Everybody was hoping, Hilbert being number one, hoping that sooner or later, hopefully within the 20th century, we will be able to prove this, and then everybody can have a good night of sleep, right? There are no contradictions in mathematics and science, and we are able to prove this, right? End of story. However, the big shock came in 1930 at a conference in Königsberg, September 7th. The young Austrian genius by the name of Kurt Gödel stood up at the conference, and he claimed that he has proofs for 2 incompleteness theorems, that's how they were called, 2 incompleteness theorems that shook the mathematical world. And they gave a fatal blow to Hilbert's aspirations. Here is what they are. First incompleteness theorem sounds like this. There is a statement in the language of number theory that is true but unprovable. There is a statement in the language, these are technical terms, if you want you can ignore them. The fact of the matter is that there is a statement that's true but unprovable in mathematics. But it is actually a statement in the language of number theory that is true but unprovable. Meaning we know it's true, but we also know that we cannot prove it. Provably unprovable. And the second incompleteness theorem is equally exciting, if not more. It says no extension of Peano arithmetic can prove itself to be consistent. Again, if you don't care for the Peano axioms or Peano arithmetic, then just remember this. There is a certain area of mathematics, a formal system of thought, which cannot prove about itself that it's consistent. And of course, this is a part of mathematics, Peano arithmetic. then it easily follows that mathematics as a whole is incapable of proving its own consistency. In other words, we will never reach Hilbert's goal, and that's provable. Provably never reach Hilbert's goal. We cannot prove that mathematics is consistent. So what? We hope it's consistent, right? We have to get this. We have to believe it. I love what Chris Leary said. Chris Leary is an American mathematician who wrote an excellent undergraduate logic textbook. I have no indication that he's a believer. I don't know. But he said this: although I believe in my heart, and this actually is supposed to be conclusion number 1. If you want, you can write it down. Although I believe in my heart that mathematics is consistent, I know in my brain that I will never be able to prove it unless I'm wrong. Are you with me? I mean, I believe in my heart, he says, that mathematics is consistent, although I know in my brain, we have proven, it has been proven, that I cannot prove the consistency of mathematics unless I'm wrong. Are you with me? What if I'm wrong? If I'm wrong, then mathematics is inconsistent, so it has contradictions. And remember, from one contradiction you can prove anything. Even from one lie, you can prove any lie. If there is a lie, then you can prove the lie that mathematics is consistent. Okay? So we cannot prove it unless we are wrong. So what? Are we really going to lose sleep over this? What are we going to do now? I mean, you go out of here and say, Dr. Szarvas destroyed everything I learned about mathematics. Sorry, Dr. Wesley. Destroyed everything I learned about science. We don't know about the foundations. It may all be false, so I'm going to quit. Well, let me encourage you not to do that. You know what? Conclusion number 2, here is why. Genesis 1:18b. And God saw that it was good. That's it. Mathematics, inasmuch as it is a part of God's creation, God doesn't create things with contradictions. Okay? So it does not have any contradictions. You can relax, go home, and have a nice sleep. It doesn't. It's just that we won't be able to prove it. But are you bothered by that? I'm not. Because I stand on the foundation of God's Word. Number 3, Proverbs 3:5. Trust in the Lord with all your heart and lean not on your own understanding. Proverbs 3:5. And number 4, great is our Lord and mighty in power. His understanding has no limit. That's Psalm 147:5. So what can we say as our conclusion? Relax. Don't worry. Use logic as a tool towards your scientific conclusions and mathematical conclusions. Use it as a tool and trust God with the foundations. John 1:1a, in the beginning was the Word. And I wanted to say thank you. But before I say thank you, I probably have 1 more minute to give this to you. It's such a fun handout, and I'm not sure if I have enough. But this is a paper that appeared in a mathematical journal. It's also found in Chris Leary's textbook. It's written by George Boulos.
Okay, while the papers are being distributed, we have
Yes.
questions from the audience for our speaker today. Yes.
Let's see here. On second, what about consistency? The whole system of logic is consistent. Is few contradictions? Do you mean contradictions within the system?
If it is free of contradictions, yeah, within the system.
Within the system. Okay.
Yes.
So in theory, then, could you have a fully functioning system within itself that has no contradictions, but contradicts a larger system, inclusive of the original system?
Sure, if 2 systems are separate, if they are based on a disjoint sets of axioms, then yes, they can be contradictory. Euclidean geometry is an example. There are non-Euclidean geometries. In Euclidean geometry, you can only have one parallel line in the plane parallel to another. But in non-Euclidean geometry, that's not true. In some non-Euclidean geometries, you can have infinitely many parallels, or zero. So yes, two systems, especially if they are based on disjoint systems of axioms, they can be contradictory to each other. Yeah.
You can have consistent systems that don't necessarily represent reality.
Well, yeah, I mean, that's the question. That
We
depends
call
on the
those-
foundation.
In science, we call those instrumental
Yes.
theories. They work well as an instrument, but
Exactly.
they may not
Yes.
represent the reality.
Yes.
For example,
Mhm.
Earth-centered solar system, you can come
Yeah.
up with models that are very consistent, but
Yes.
we feel they don't represent reality, but they can still be very consistent.
This is, thank you. This is why you need both things. You need the right foundations and you need a consistent system if you want to reach correct conclusions.
So, can you use logic to prove that God doesn't exist? Or
That-
that he does exist?
That's an interesting question. All I know is that Gödel, who is one of the greatest geniuses in logic, in my estimation, who ever lived, he does have a proof. He does have a proof of the existence of God. I don't think it can be done, but if anyone can come close, I think it's Gödel. And he does have a proof, which shortly before his death, he said that the proof was good. I'm going to admit something. I'm going to confess that I haven't yet studied the proof because it is so deep that I would need, extended amount of time to even understand it. So I cannot speak for the proof. All I know is that Gödel was a genius. I don't think you can prove, I don't think you can prove the existence of God, but I think Gödel's proof is probably deserving of your attention if you have a few free hours or days or months or years, if you want to understand it. Thank you. Thank you.
There were several attempts to prove that mathematics is consistent, self-consistent,
Yes.
between the time of David Hilbert of 1900
Yes.
all the way up to the time of Gödel in
Yes.
1930. And these were famous attempts to prove the self-consistency of mathematics.
But only partial. I mean, no one got to any conclusion. It was just, thinking, okay, we can probably proceed along those lines, and then some partial results were achieved, and then they hit a roadblock, and something happened. They were only attempts, non-successful. Yes.
Creation doesn't contradict itself.
No.
Mathematics emulates creation.
Mhm.
That's all. It's an example of creation.
Mhm.
Examples do contradict themselves.
Examples of what?
As a whole,
Yeah.
if you use an illustration and you eventually at some point it breaks down.
Mhm.
So, is my logic correct in thinking these things?
If you're in a formal system where the underlying axioms are not self-contradictory and your formal system is sound, logically speaking, then you will never reach contradictions.
Mathematics is made by man. Creation is made by God.
Yeah, well, I submit to you, I believe that mathematics was made by God too.
Yes.
I think mathematics is the language that he used to write the laws of the universe. Man discovered it, and of course man, we introduced names for things, such as why do we call the integral an integral? We introduce names for things, and I think it's a gradual process of discovery of laws that were already in place by God, as opposed to math being a human creation, like you keep creating stuff, human creation, that people create. I believe it's already in place. We just, discover it in as much as our God-given wisdom and talents allow us to do so.
Okay, we have a final question? Yes?
So would you say then that math is, to an extent, kind of like a microscope, I guess, a tool we use to understand I guess you would say math, again, a base logic that God created originally with the universe. We use integrals, things like that, in order to understand and use that base logic, kind of.
Yes, we use the tools provided by mathematics to understand the created world around us. Yes, that's correct.
Okay, if you'd like to join us for lunch, we'll be over in the Joyce Room or the Corner Cafe. Otherwise, otherwise we'll see you here next week. We have a single person here from Easton talking about Six Sigma process. So let's thank our speaker again.
Thank you.
Yeah, so,
Thank you. Thank you very much. That was good.
Thank you.
all right, I'll see you
Thank you, brother. Great to see
later.
you.
Yeah, are you gonna come by my classroom before you leave?
Which one is the class?
Hopefully Gary, he'll take me there.
Okay, all right. Yeah, I will. I will. Your
Yeah.
class runs from 12 to what?
1:20. And I think you guys have lunch. Hopefully they'll keep you for an hour. Just come by. Do you have class to teach today?